My name is Eduard Muresan. I'm here on behalf of Bitdefender to talk to you about CIAPO. Now, CIAPO stands for Code Injection via Arbitrary Pointer Overwrite. It aims to be a technique that wants to achieve execution in a manner as obscure and as stealthy as possible by refraining from using an execution primitive. Now, as I said, my name is Eduard Muresan. I've been a security researcher for Bitdefender for the past 6 years or so. I think that turns into 7 this summer sometime. I am passionate about low-level systems programming, hacking in general. I actually am currently developing a microkernel that I quite enjoy writing bugs into. You wouldn't believe how many, actually. And I have a high interest in injection techniques. The reason for this is because my boss sometimes, 3 years ago or 4, tasked me with researching injection techniques for the purpose of detecting them into our products. And I've been hooked ever since because I think they're really cool. Now, when I'm not working or hacking in general, I like to enjoy relaxing with some mythic raiding and mythic dungeons in World of Warcraft with my guildmates. And relaxing is not quite the right term for that. Now, what will I be talking to you today? We will start with a brief history of process injection, where I'll be presenting what process injection is, what it is used for, and a couple of basic techniques and some more advanced one. Then we'll move on to the CIAPO methodology, where I'll describe how it works in general. I will go over some interesting pointers that I've overwritten with CIAPO. And then we'll talk about some existing mitigations, and finally a demo and maybe a Q&A session. Now, what is process injection? Well, process injection is a method used by malware to execute arbitrary code within the context of a separate live process. Now, why would we use process injection, or why malicious actors would use it? Well, the reason is simple. Executing a process within the context of another one might evade process-based detections. Think of a complex program like a browser, for instance. Now, some of you might know that a browser doing some shady business is just another Tuesday. It just happens. And we tend to ignore it when developing defense solutions because it's for legitimate purposes. However, a process such as w20xyz.exe might not have such legitimate intent. So then it would want to execute its malicious code within the context of the browser, for instance. Now, how does injection work? It has a couple of building blocks, one of them being an allocate primitive, a write primitive, and finally an execute primitive. Now, an allocate technique, as the name allocate primitive, as the name suggests, is used to allocate or reserve space in the address space of the target process. This is usually done using a legitimate API, and it can also be implicit, like you can just use code caves or slack space between the process sections or shared memory. The write primitive, again, is used to write your payload to the target process. This also might be legitimate. They might have, because it's usually used for legitimate purposes, like inter-process communications, for instance. This also can be implicit, like writing to a memory map or to shared memory. You can just do this by using a simple mem copy. Now, allocates and writes are usually trusted by defense solutions for the reasons I said earlier. They have very legitimate purposes. Now, execute primitives, on the other hand, are not so legitimate. The basic create remote thread execute primitive, for instance, in the MSDN documentation, it states that its purpose is for debugging purposes. And malware doesn't debug processes, does it? Now, all of these are usually highly monitored because we'll see later. Now, let's piece everything together and try to craft a simple injector. Here we can see the allocate primitive, the write primitive, and the execute primitive. This is the classic remote thread injection. I'm sure many of you know about this. It's probably older than I am, and uses virtual alloc X to allocate, write process memory to write, and create remote thread to create a remote thread and execute the payload. Now, a defense solution will basically always monitor this specific execute primitive. So for that reason, black hats will try to find a different execute primitive that might evade solutions. Well, and that's how they come out with another execute primitive, mainly QUser-APC. This leverages the asynchronous procedure call system of Windows, where this API will add a function pointer to a queue over thread, and whenever that thread enters an alertable state by either calling sleepx or wait for single object, it will pop a pointer of that queue and simply execute. Now, there's an implicit problem with execute primitives. As I stated for create remote thread, they will be highly monitored. They can also be blocked depending on the execute primitive. And depending on the execute primitive, it might be traced back to the attacker to get a full history of the chain of attack if you want. Now, coming up with a new execute primitive every time one gets monitored becomes a cat and mouse game. The black hats will find a new shiny execute primitive, use it in an attack, and the white hats will find out about it, block against it, and so on and so forth. So what if instead we were to do something a little bit crazy? What if we were to just remove the execute primitive? Because we don't actually need it. In order to do so, let's take a look at the portable executable file format. Now, we do not care about the DOS header, the DOS stub, or the section table for now. We're interested in the anti-headers. Specifically, we're interested in the data directory within this header, because there we can find an interesting directory called the TLS directory, which contains, amongst others, this pointer to the address of callbacks. Now, for a program that uses thread local storage, more specifically thread local storage that actually needs to be properly initialized like a C++ class, this will point to that very pointer. And whenever the loader will load the program into execution, it will scan for this TLS directory and point to it somewhere in memory. There's going to be a list of entries for each module loaded into a process, and for each module there will be a pointer to the TLS directory. What's cool about this is that it's a pointer to the in-memory image, meaning if you manage to somehow write the callback that's here, it will be executed at some point whenever the TLS callbacks get executed. Now, when is that? Whenever a thread creates for the constructor, or whenever a thread exits for the destructors. So you can see that just by overwriting this, we can aim to achieve execution at some point. In a similar fashion, if you go back to the anti-headers, there's also a very interesting field there called address of entry point. When a module is loaded into memory, the loader will search for this and insert it into an per module entry of this LDR data table entry. Now, if someone were to overwrite this entry point, they would achieve execution in a similar fashion. This usually points to the DLL main of a DLL. So as per the MSDN documentation, there's going to be called when on process attach, process detach, or thread attach, thread detach. So whenever a new thread gets created or exits, we will achieve execution again. Now, for something completely different, The people who researched process Mockingjay thought it would be very cool if they would find a pointer, not a pointer, a DLL, that would have a default read, write, execute section. The purpose of this section is that they will also remove the allocation primitive, because they just didn't want it. Now, it would also be cool if this DLL would be loaded in some system processes, or some processes. And it would be even better if this section would get executed at some point naturally, so you don't need an execute primitive again. Turns out there is such a DLL and such processes. msys-2.0.dll gets loaded into every POSIX emulated process on Windows. And that's their technique in general. You just override that read, write, execute section and let SSH run for some point, for some time, and at some point, you will achieve execution. Now, you can probably see, oh yeah, you would first overwrite the read, write, execute section with your payload. I forgot. Now, you can probably see that there's some problems with overwriting these or manipulating these specific pointers. And these problems are the same ones we had with execute primitives. When execution happens, they can check for these pointers to see if they are clean or overwritten. And this, again, becomes a cat and mouse game. A black hat will find a new shiny pointer or callback, overwrite it, and then the white hat will find a way to monitor this and block it. Which brings us to the CIAPO methodology. Now, as I said, CIAPO stands for code injection via arbitrary pointer overwrite. And the name basically says it all. That's what we are going to do using CIAPO. We're going to first open a process. Most of you are probably familiar with this image. Everybody who took a, operating system class probably has seen this, the virtual address space of a process. And we have the heap, the stack, and the image, where the code and data resides. Now, first thing first, we want to inject our malicious payload within the process memory using an arbitrary read and, allocate and write primitive. And those are the only primitives that we are going to use, actually. Now, we shift our focus to the heap and the image, because what we're interested in are arbitrary pointers. Not only arbitrary pointers to executable memory, to functions. And what we want to do is search for these. Whenever we find one, we are going to override them with the address of our payload. And we are not going to stop at one pointer. We are going to go over another pointer and another pointer until eventually all your pointers belong to us. I like that you got the reference. Give me 1 second, please. To better exemplify this, let's take a very simple piece of code that uses a function pointer. Now, I know function pointers are scary, but just bear with me. We have a function pointer in the .data section. We initialize this function pointer to sleep, and then we just call it a bunch of times. Now, this gets compiled to this piece of assembly code. On top is going to be the initialization of the pointer, and here is the while loop. You can see that the way the pointer is called is using an indirect call, that call RAX that's highlighted. I don't know if you can see it. Now, indirect branches are the main entry point for achieving execution in CIAPO. The reason for that is that an indirect branch, unlike a direct branch, will dynamically determine its target address at runtime. And it will usually do so by loading the address from a memory location. And as stated earlier, we want to control those memory locations. Expanding on that, these are usually generated by the compiler in most processes, most legitimate processes. And at some point, it's guaranteed that they will get executed. So let's look at the debugger view of that sleep variable. This is before CIAPO would attack the process, and this is what happens after it attacks the process. This is the pointer to our payload. And as we saw the loop, eventually, this will be executed, and CIAPO will achieve execution. Now, let's look at how we would find, or where we would find executable pointers. In the image, we can expect to find a section for read-only data, for read-write data, or for code. If we look at the read-only data section, we can find a bunch of interesting stuff. This is mostly either constant strings that you might use or constant global data, but it's also the home of some data structures that are generated by the compiler itself. For instance, the import address table will be filled with the addresses of any imports from any modules you might want to use, such as getproc address from earlier, where we would initialize the sleep pointer. Now, those of you familiar with C++ would know about virtual function tables or virtual method tables. They're just a big array of functions that are going to be pointers to, well, the methods of the class. Now, a live object of that class will have a pointer to this virtual method table. And in fact, if you remember from a couple years back, extra window memory injection used to overwrite that pointer, so of the C-tray object. And instead of pointing to its normal virtual method table, it would point to a malicious virtual method table. Now, overwriting pointers in read-only data is fun because there's a lot of them. And also, it's very easy because they're very nicely structured by the compiler. But it also can be suspicious. Defense solutions might just know how read-only data is supposed to look like, and yeah. Moving on to read-write data. Now, this section doesn't contain such nicely organized pointers because it's going to be generated according to whatever the programmer wrote. It is what it is. But we can expect to find some function pointers here. Like, imagine you want to use some anti-DLL API that you find on Google, but it's not present in the system headers that you're compiling with. But you know it's exported by anti-DLL. Well, you would just define a global pointer like psleep earlier, initialize it to whatever export you want, and then just move on with life. And that's exactly the kind of pointer we're trying to find and overwrite with CIAPO. Now, when I was testing this, and I usually test my stuff on the Explorer process, I don't know why, but it's fun. I found out that at the very beginning, I mean, I was overwriting some pointers at the very beginning of the data section, funnily enough. And these were pointers to some comctl32 functions. Now, I found out that Explorer keeps this huge array of function pointers that it uses to dynamically bind to comctl. Using these wrapper, like DSA delete item, it will bind to somewhere. As you can see, it will just, when uninitialized, it will just be a -1. We'll check for that, and then get the function from comctl32, and just call it uninitialize. Now again, data pointers are fun, and there's plenty of them. This is only an example from the Explorer process. But even more fun is if we take a look at the heap. Now again, the heap will not be as nicely organized, but we can expect to find some structures, some dynamic arrays. We can expect to find a lot of things depending on your target process. Now, the pointers on the heap are not usually going to be just dangling around like they are in the data sections. They usually will be contained within some structures where it makes sense for them to be. One such example, or more examples, would be these 3 pointers, which most of my executions when I was targeting the heap would be from overwriting these. Now, turns out these are callbacks within thread pool structures. Now, thread pools are just a system in Windows for multitasking, obviously. And all processes will have a thread pool. And they support multiple work objects, like timers or wait objects, advanced local procedure call objects, etc. And they are structures, exactly what we are searching for. And turns out these were just callbacks within some worker objects. Now, funnily enough, there is another injection technique called thread pool party. I think it was revealed at Black Hat a couple of years back. It's a very cool technique, and I'll tell you why. What it basically does is abuse these objects by first allocating space for one object, then using a write primitive, maliciously craft an object and insert it into a thread pool queue. And again, at some point, it will be executed. Now, the way CIAPO differs from that approach is that we don't really want to craft any thread pool objects. We want to just overwrite whatever existing thread pool objects are there. We want to take control of basically everything. Another interesting find on the heap was in this. The sort compare string, which doesn't really make sense to be a function pointer, but it is. And it turns out this is part of a system from Windows called National Language Support, where depending on your current locale, you would sort strings differently, and that makes sense. There's different ANSI encodings for different languages. And what happens is that this is controlled by a registry key. And depending on the value of that registry key and the loaded locale, it will load a DLL to deal with sorting strings on or locale-specific string stuff. Now, again, I found out that there was another technique abusing this for DLL injection, as you might think. Because if you override that registry key with a DLL of your choosing, and then set the current locale to whatever you want it to be, you can just load that DLL into the target process. And you can do that by using set thread locale, funnily enough. Now, again, CIAPO is not interested in that. We just want to take control over the structures on the heap. So we'll just find that pointer to kernel 32 and overwrite it with our own pointer. And then just have fun. Wait for some string compare to happen. And in the Explorer process, there's a lot of string compares. Now, with injection techniques in general, there are usually some mitigations in place. One such mitigation is the Intel CET-IBT, which stands for Control Flow Enforcement Technology, and IBT is the Indirect Branch Tracking part of CET. There's another one, Shadow Stack, but we don't care about that right now. So how does IBT work? Well, if you have an indirect branch and the feature is enabled, it will put the processor into a waiting for branch state. And if you just jump to some arbitrary piece of code, it will generate a control protection fault, crashing your program. But if you instead jump to an end branch instruction that's instrumented before your arbitrary code, it will just let you execute in peace. Now, this requires compiler support. It is used in Linux system, I believe. I think GCC by default builds with end branches on targets of indirect branches. But Windows doesn't use this currently. Instead, Windows uses CFG, Control Flow Guard. Now, to exemplify Control Flow Guard, let's take a look at the previous piece of code, this pslib. This, without Control Flow Guard, will get compiled as we saw earlier, with just an indirect branch. But if we enable CFG using the compiler flags, it will be compiled to something entirely different. There's no indirect call to RAX. Instead, there is a call to this guard dispatch icall fptr function. Now, when this will get loaded into memory, guard dispatch icall fptr will point to an ntdll function that will check whether the target address is supposed to be executed or not, if you just inject random code into a process that's not really marked for execution. But it does have a flaw, though. And that flaw is the fact that just-in-time compiling exists. And sometimes you would want to execute arbitrary code on the heap for legitimate reasons. So there's an API for doing just that. You can mark your injected code as valid for execution using CA set target for execution. Now, let's take a look at CIAPO in action. Here, I will target the Explorer process, again, for your enjoyment, using a shellcode that would just spawn a Notepad process and then return to Explorer to let it continue executing normally. Now, you might wonder why not the classic calculator. Well, for a few errors now, you cannot really spawn a calculator using WinExec. Somebody decided to take all the fun out of it, exploiting, I don't know. Yeah, let's take a look at what happens. I don't know why that happens, by the way. It used to work. But it's just a command line that targets the Explorer process with that speed. I don't know why this shows like this, but the important part is that we can see a plethora of Notepad processes happening because execution happens quite instant, and yeah, there's a lot of indirect branches that we have targeted getting executed. It's quite beautiful, isn't it? Give me 1 second. Well, to wrap things up, detecting injection attacks by only monitoring execute primitives is, in this day and age, is still necessary, but is not sufficient. It's not enough that you can catch the execution primitive of extra window memory injection if you cannot catch thread pool party executing normally, or CIAPO executing normally. Now, injections aren't a security boundary. They are not vulnerabilities or exploits, but they allow attackers to evade security solutions, thus increasing the mean time to detection. For this reason, having a comprehensive approach to detecting and preventing injections is mandatory to ensure individuals and organizations remain unharmed via defense in depth. This is the reason why white hats are continuously developing injection techniques and mitigations, like CIAPO. It is better to be prepared today for the attacks of tomorrow. To this end, CIAPO pushes forward the state-of-the-art, demonstrating that attackers might use brute force approaches to overwrite random functions. Thank you for listening. If you have any questions,
when looking for pointers to overwrite, do you have like a predefined list of these are like pointers that usually are found there, and or you override them, or do you overwrite anything that looks like a pointer?
It's more simple than that. You can just iterate over the address space. You can like parse the PE of a target and get to the data sections, and then you can do one of two things. You can either call virtual query X and see that the memory protection is executable, or you can just see that it points to an executable location within that PA file or the modules that are loaded. You can take different approaches to this.
Thank you.
Yes.
Okay, thank you for the presentation. Did Bitdefender's EDR catch this thing?
Yes, Bitdefender defends against most injection techniques,
Yeah.
including CIAPO.
Yep, okay. But did you get to some EDRs not catching this because you're trying to evade, right?
We haven't tested against any other EDRs because that wasn't the purpose of our solution, of this research.
Yeah. Okay, thank you.
Have you thought of ways to like reduce the noise that CIAPO makes, like running the shell code on every overwritten pointer?
Yes.
Kind of noisy.
Yes, and you don't have to do that. The title is arbitrary function pointer, not all function pointers, right? For the purpose of the demo, I just overwrote all pointers, but in reality, as an attacker, you would want to be a little more stealthy. As you said, it's a lot of noise to do it on everything. So for instance, you would filter out some known pointers. Like if you just blindly target the heap, you would end up overwriting the thread pool pointers or the NLS injection pointers, which would be monitored by now, even though they are relatively new techniques. And also would overwrite LDR data pointers to the entry point and so on. You would use this basically in a more targeted attack where you would know that this process uses a lot of function pointers in its code or uses a lot of callbacks on the heap and filter out what you don't want to get executed from.
I can think of an example, like if you were to inject the worker process for the IIS web server, that might use a lot of thread pools, so
yeah,
you might try there. Okay, thank you.
Well, thank you all for coming, and I hope you have a pleasant rest of the DefCamp.
Oh.
You're free.